Yeah, it is part of the vector, matrices, and simultaneous linear equation. They are all integral part under the title called linear algebra. Okay.
Yeah.
Because in this algebra, there's only involved linear equation. That's issues. Okay, that is the key.
Yeah.
Oh, x equal to y. Okay, let's double check.
Yeah.
Yes, you're right. Okay. Now, if x equal to y, how to write its second eigenvector? Yep.
It was
X, y, yeah.
just
That's
equal
right.
to you could use y again.
Use y to solve x, that's right. And then
That means you only have one constant to figure
so
out,
that's the second vector, see? Can you see? So as a result, you solve it. So xy equal to what? Remember? What's the second? First 1, 3, right? 1, 3. Yeah, 1, 3. 1, 2, 2, sorry.
1, 2, 1, 2.
2, 1. It's
2, 1, yeah.
2, 1.
Yep.
I hope this, for example, give you some confidence how to deal with this problem. Okay.
Yeah.
Because when you study, this is just 2 by 2. But if you know the principle, and if you I don't know if you want to become of course your object to become doctor, right? If you want to become engineering, people just can learn some computer language. They can deal with any dimension of simultaneous equation.
Oh yes. Oh
yes.
damn.
But anyway, but knowing this is the method is very important. You see, the linear equation is so important. Do you know why? Because that is the first approximation to study any phenomena. If you start linear equation, if you just focus on very small part of the change, right? All the change can be described by linear equation. You agree? So the idea is that when you will know, we know that in the future we will study very complicated curve, right? But if you just look at it very locally, if you look at it locally, can you see? If you only see this part, can you see? Can you see it is linear equation? Can you see? That's right.
Oh yeah, because
so
it's a curve and
that's right. And also if you go that part, you can also see the straight line here. Can you see? Yeah. So that's why we there's a special branch in mathematics called linear algebra. Okay. And you can use this to solve many questions. So in the future, what you will see, so if you have for example, I just take examples. So in general, in the future, if you have this is A11, do you remember that matrix? A12, A22,
yep.
And AN1, and this is A1N, right? And this diagonal, this is called diagonal part, 2, 2. A33 until ANN, okay? So so this is just the elements. So in the future, if you see these things happen, you know that in principle, we should be able to solve it by matrices, okay?
Yeah.
Can you see? So that is how we solve the linear equation by use matrix method. So this is, it's just in general, that's a C1, C2, and Cn, okay? So that is a simultaneous equation, simultaneous linear equation.
Yeah.
You see that? That is that's a general form. So this is a general form of simultaneous equation.
Yeah.
So it's not abstract. So it's no longer abstract anymore to you. Do you agree? Although we only just focus on 2 by 2 at the moment. Just remind you to give you, in the special case, we should see that we will choose this form. You see, we'll choose the matrices here. We got a particular value, which is just equal to lambda. This is just like the scalar. Lambda is a scalar, do we?
It's a scale. Yeah, it is.
So in a special case, in a special case, you will get this eigenvalue equation. It's called eigenvalue equation. So from there you can work out the eigenvalue and eigenvector. Okay. So another thing I think we'll discuss when we discuss vector, you have to, so what does mean if we got eigenvector? So basically what you can say is you can, if you know if the eigenvalue is given, is found, if eigenvalue and eigenvector are obtained. So what we can write? What can we write here? What can we write?
If eigenvalues.
Yeah. So basically, can we just go? Yeah, just talk about A first. We just use this example, okay? You remember A, -1, -2, 4, 5, right?
4 and 5.
Yeah.
Yeah.
So if we know eigenvalue and eigenvector, what does it mean? Can we simplify? Can we simplify this? Can we rewrite this form?
Rewrite like.
Yeah.
Rewrite the what?
So basically, if this is matrix, right? This is matrix, and we found the eigenvalue now. Do you remember? Can you write it down? So eigenvalue I'm equal to 1, and eigenvalue equal to 3, equal to 3. Okay.
Yeah.
And this is the eigenvector. Eigenvector is what? Eigenvector 1 is 3, 1. 3, 1.
2, 1.
Oh, 2, 1. Sorry, 2, 1.
Yeah.
And eigenvalue, they are corresponding. So from there, we can solve that. And eigenvalue 2, we equal to what? 1, 1? 1, 1.
Yep.
Okay. Now, because they both satisfy this equation, right? So in other words, that implies, because this implies that if you have A, multiply his first eigenvalue, x1.
Yeah.
So what do you get?
Lambda.
You get
1
times x1. Can you see?
x1, yeah.
X1 here, right? Okay. Now, can you write them together? I'm not trying.
Right. What together?
Hang on. This is not what I mean. So, probably this is not right. Can we just consider a transformation? Because I can give you higher level math if you want to know more. So let's consider consider a transformation, okay? Transformation. So in other words, can we call the transformation? Can we use which number?
B R.
Can we use B? Yeah, you can use B. Yeah, we can use B, right? B is also matrix. B is a matrix. Is also a matrix. Okay.
Yeah.
We just assume that the matrix after we time B. So basically, what we use B on both sides. If we just can we write this form? Have you seen this form? So this B inverse and B, right? We just consider this case. Then that will become purely as a matrix like this. Lambda 1, lambda 2, 0, and 0. What would be the B? What would be the B?
So A is the same matrix as before.
Yes.
B is a transformation.
Transformation matrix to be determined. To be determined. To be determined.
And it does that somehow. Oh.
Yes. So that just means a transformation, right?
So it gives you lambda 1 and 2.
Yeah. So can we just first can we time B on both sides? We time B, okay? If you time B, you got a unit vector here, A, B. You get a B times this vector, can you see? Lambda 1, lambda 2, 0, and 0.
Yeah.
Okay? So because here what we use here is a B times B inverse, we're equal to unit vector, right?
Yeah.
Can you follow me? Yeah.
Yep.
So in that case, can we just solve the B because we know A? okay, can we solve the B?
Okay.
So in other words, can we write that for you? So that means the A is -1, -2, 4, and 5, right?
Yeah.
And we don't know B. Can we just call the A, B, C, D? A, B, C, D,
yeah.
right? A, B, C, D to be determined, right?
Yeah.
Okay. And it will equal to, can you see? It will equal to B, just use A, B, C, D. Can we use A, B, C, D?
Yep. And we know the values of lambda 1 and 2.
We know the lambda 1, yeah, I'm going to say that's 1, 1 is 3. Can you see?
1 and 3, yeah.
Yeah. Now, can we use this equation to determine the A, B, C, D?
Yep. All right. So you got
the product of two matrices. It's too crowded here.
It'll be fine, I think. C.
You got yeah.
Oops, sorry. And now,
can we, because in each matrix we can build one equation because these two sets are equal. I don't know. We probably will double check, but before I just tell you method, okay? So this one must be equal to A. Can you see? And
I get that.
So how many equations we can build?
4, and
yes.
You got 4 unknowns.
We got 4 equations. Okay.
And
do you want to save? Do you want to save this page?
Yeah. Let me just quickly save it.
Yeah. So because we were going to use this page to solve this one, so what I do is I clean up the first part. Okay.
Yep.
First part. That you can use this page here. All right. You can use upper side to continue problem solving.
Yep. Sorry. All right, let's do this. So then you got
you got 4 linear equations, simultaneous equations, right?
Yeah. Let me just move this. All right.
Yeah. Can we solve the A, B, C, D, or 4 elements for the B?
So for 1, it's A equals 2C. So sub negative 2 to C. Oh wait, what does this show?
All the C, right?
Yeah.
So you substitute A to C to 3, right? So you got the CCC.
Oh
so
yeah,
then you solve the C. You should be able to solve the C, okay? That allowed you to solve the first unknown.
You just give C equals C.
Are you sure? Oh, you can't solve that because you got C is undecided, right?
Yeah.
It's undecided. Oh.
There's no constants either.
Oh, let's double check this question. So basically we got a B matrix A, B, C, D times this matrix. And can we double check this formula here? Can we just redo that part? Can we double check that a little bit slower? So in this way, you will learn that you will learn some idea in algebra, in linear algebra. Can we just double check that? So let's double check the matrix. This matrix is -1, -2, right? -1, -2, 4, 5. Can we finish this again? We'll do this again. So basically you got -1.
Yeah.
You just -1 is -A, right? -A, -A. So this first element. So -A
Plus
times 4 times
C.
C plus 4C plus 4C. That's all, right? 4C.
Yep.
And the second will be 4A, right? 4A. No. Same that. -B, right?
-B plus 4D.
-4D plus 4D plus 4D. Okay, we just do this slowly. Then this one, we just compare with that. So this one, the second row is a -2, -2A, right?
Yep.
-2A plus
5C.
5, 6, 5B, right?
5C.
No, 5C, right? 5C, this one, 5C plus, right?
Yep.
Plus
5C.
And the last one would be -2 times B, right? -2B, right?
Yep.
And plus
5D.
5 times D, right?
Yep.
What's this? This is 5C.
5C
times D. Can you see? 5C.
Yep.
5C, you will be 25 CD, right? Is that right? It's non-linear.
No.
Non-linear. Oh, you just use, no, just, so this is not right. I use bigger here. Yeah, just use the 5 times D, it's 5D, right? It's 5D.
Yeah, it's 5D.
5D. Oh, you're right. So this part is right. This part is all right.
Yeah.
And is equal to that side. So when we can say A times 1 is A, right?
Yeah.
A times 1 is N. And B times 0 is 0, nothing, okay?
Yeah.
So then you got A times 0 is 0 and B times 3B, right? Yeah, you're right.
Yep.
3B. How about this one? C times 1.
C times 1.
Just C, right? Just C. And then use C times 0, D times 3, 3D. Yeah, you're right. Yeah, what's wrong? What's wrong with our equation? Doesn't matter, we just do it again. Okay, can you do it again? Just do it again.
So I was gonna.
Yeah, this time we'll be careful. So what did you do? So last time you just solve the first one, solve the A in terms of C, right?
Yeah.
So first question give you C and A in terms of A. Yeah, we still have trouble, right? If that's so, we can't solve the C. That's interesting.
Yeah, it's weird.
It's a weird question.
Is it because we don't know B? We should normally be given B, given the trend.
Basically, I give you result. Can we just check this backward? Okay. So in general, I just give you the result over this block, this here, and then we will check what's going wrong here. Okay. So basically, if you have lambda 1 equal to 1 and the x first eigenvalue is what? Is 3, 1, right?
2, 1.
2, 1. Sorry, 2, 1.
Yep.
2, 1. And the lambda 2 will equal to 3. And the second eigenvalue is 1, 1. Okay. So if that is the case, B will be simply equal to, just put them equal to 1 and 1, 1.
Yeah.
Can you see how did I do that? I just give you the clue. So this is just, can you see, this is, so this is 1, can you see? This is x1.
So.
That is correct. This is the answer, though. This is just answer. But we'll move backward to check what's wrong with our calculation. So this one will be this one.
Yeah.
Okay. Can we just use this equation to check if that satisfies this equation? So this is A, B, C, D. So what is A, B, C, D? This is the question. Can we just use our value to use this simultaneous equation?
So basically for B.
B is 1. A, B, C, D, A is 2, other are 1.
But for the B matrix, how did you know it was like, how did you like, you put the two vectors together?
Oh, well, that is algebra. So for people who don't know how to determine the matrix B, that is how how the students were told, okay? So you can build a transformation. But the idea is here, can we just use this to see, can we go back to the, matrix form? Okay, do you remember the matrix form?
For which one?
So basically this equation, so this equation come from the matrix form, which is said that is A times B must equal to B times the matrix called lambda 1, lambda 2.
Yeah.
Agree?
Yeah. Yeah.
So can we use this one to check if this is correct? Use this result. Okay. Okay.
Okay.
Can we just find A, B first? Can you work out A times B first?
That's it. Oh, okay, I see what you mean. So, but can we use these simultaneous equations because we've already expanded them correctly?
But this is easier because got the number. Or you can also you can also substitute. That's right. You can substitute that. You can substitute. Yeah, you can do substitution by just substituting A, B, C, D here. So A equal to 2. B equal to 1, C equal to 1, and D equal to 1. Okay, that is the two elements of this.
So like A equals to 2, and C equals to
1. Yeah.
So then, therefore, it's negative 2 plus 4 equals 2 negative. Oh,
yeah, it's satisfied.
It's all good.
Yeah, the first one good. How about second equation?
Yep. So then,
they're all 1, right? Negative 1.
Yeah.
2. It's also 2. How about third one?
Yeah. A equals to C equals 1. And then for then.
Well, whatever happens, this is very important. So today we're learning something new, that is how to work out that transformation matrix if we know the eigenvalue and the eigenvectors, right?
Yeah.
Well, we'll go back. This is just something. Perhaps these four variables are not independent. That's the only reason. But before we go to check that, can we just let you know that the important message is that if you have a transformation B, right? If you got a matrix here, and if you know this transformation B is inverse and is B, so by doing so, you can also obtain matrix which only have diagonal elements.
Diagonal elements.
Yeah.
Only diagonals.
Yeah, because yeah. So this is called
Could you please repeat that?
Yeah. So if you know the B, the transformation there. In other words, for the given A, there exists a transformation matrix B. Okay.
Yeah.
By doing this transformation, then you will obtain a diagonal matrix. Do you want to write it down? Do you want to write it down?
Yeah.
So this diagonal. So for
write it.
For a matrix, for the matrix, okay. And there exists a transformation matrix, yes, matrix, so that B inverse A times B will give you a diagonal, okay.
Yeah.
So this is M1, lambda 2. That's be called a diagonal matrix. Okay. I hope that this is beyond your syllable, but I think it is important. This exercise is important to you to understand. The diagonal. So any matrix, for any matrix, in principle, in any matrix, okay, there exists a transformation matrix. In addition, I have to write more thing.
Yeah.
That's something. So we'll go back to see what's wrong with this simultaneous equation. But I will tell you the idea first. Okay, this idea is always important. So basically, in this case, transformation. So therefore, which makes this first idea. Okay, the second idea is that the transformation matrix. You know transformation now. Any matrix, a square matrix, can be considered as a transformation. All right.
Any square matrix.
Yes, can be considered transformation matrix.
As a transformation.
Yeah, transformation matrix.
Yeah.
Can be obtained.
Yeah.
By if the eigenvalue, and more important, eigenvector, yeah, are known.
Yeah.
It's just the other way around. You see, when you study mathematics, either you go to go to one direction, such as we can either expanding, right, or you can go backward. You can go factorizing, right? You see, in mathematics, so you have to know now. Mathematics is always to rewrite the form of the given expression, right? You can go backward. You can move forward. So in other words, if the eigenvalues are known, then these vectors, so these B, the transformation vectors, chemical transformation will be simply equal to, can we write into this? Can we just use this eigenvalue 1? Eigenvector?
Oh, the vector 1 and vector 2?
Yeah, vector 2, can you see?
Oh, okay.
That's very important. So in this particular case, we know that in our particular case, it is 2, 1, 1. Okay?
Yeah.
In this particular case. So these are important ideas in linear algebra when you start matrix.
When we define eigenvector, right, you said it's like 1 or more per matrix. So since when you solve, you get quadratics, is it always 2? So like, can there be more?
No, there's more than, their maximum is 2. That is determined the dimension. If it's 2 by 2, the maximum value, eigenvalue is 2. Okay. 2. But sometimes you will encounter that the 2 eigenvalues are both identical, are the same.
Oh yeah.
So this is similar to the quadratic equation. You see, when you have a quadratic equation, in principle, the maximum solution is 2, right?
Yeah.
But sometimes you get an identical one. See?
Two identical answers.
Yeah, two identical answers. Okay.
Oh, yeah, I know what you mean.
So otherwise, if you just go to the 3 by 3, if you have the 1, 1, 2, and 0, 1, 3, and 0, 2, 4, for example, right? So how many eigenvalue would you expect to obtain? How many? Hello? Connection problem. Yeah.
Hello?
Yeah. I lost your voice. Can you hear me?
Oh, can you hear me now?
Yeah, I think something wrong with your mic.
My headphones died. Like they just stopped working for some reason. I charged them, but they're just.
Oh, I see.
Oh man.
All right. Well, that's why I suggest you see when you do online tutoring, you have to prepare proper stuff. Yes.
Oh yeah. These. I think I'm probably need new headphones. These are faulty. Like I remember a couple lessons ago, they died before the lesson. Like they just died.
Do they use battery for headphone? No, I don't think so.
Oh yeah, these are Bluetooth, but like it's Bluetooth and you can charge it, but like it's not wired. The wire doesn't let you speak.
Oh, okay.
There's no microphone.
Yeah,
option,
you see, so basically, I understand your mom is worried about the online tuition because if you don't have proper headphone or earphone, we do have trouble. You see. But anyhow, so 3 by 3 is in this case, in principle, you should get a 3 eigenvalue, right?
Yeah.
But
maximum, right?
Maximum is 3. Maximum is 3. So that is why the reason I teach you this part is that I want to know the ideas in study matrices, right?
Oh yeah.
So once you know this the ideas, we can do other things. For example, perhaps today will be the I don't want to put too much info content in these topics, right? But I think that will be helpful for you. Now, if we still have the time, can we just go back? What's wrong with this simultaneous question? Does that mean we have to? This is correct, right? This simultaneous is correct. We have.
Yeah, I don't. Can you solve it without a constant? Because otherwise you're just solving the variables in relation to each other.
I think these 4 variables are not totally independent. Do you agree? So that is again, this is the issue in linear algebra. Sometimes you got more equations than necessary, right?
Yeah.
You got more equations necessary. So perhaps we have to choose. In this case, we have to choose one element. Let's just look at this again. You just have to think. How about if you just solved A, you cannot solve the C.
Yeah. Like they're quite dependent on each other. I mean, like.
Yeah, C and A are dependent on each other, right?
I think it's the same thing applies to all of them because there's no like constant number. It's just the variables.
Just variable. My question, can we just double check that? Does that the first equation equivalent to the third equation? I have the question. Can you answer my question? Is the first equation equivalent to the third equation? We just solved it. Can we just solve the A and C? Can we just solve the A?
Okay.
If they are identical, these 2 equations are not independent, you see.
Yeah. So we know. Should we like check in terms of?
No. We just solve it. We just solve A in terms of C. We just solve A in terms of C from both equations. From both equations.
Okay. In the first one.
Yeah.
A is equal to. Okay. Yeah. Let me do it. Number 1.
Yeah, x2c. Okay. Can you from equations? No, 3. Equation 3 from equation 3. Yeah.
So it's Um. Hmm.
Yeah.
Oh yeah.
Yes,
Same
they're
thing.
not independent. That's interesting.
They're,
They're
yeah.
not independent. So obviously there's some independent. How about well? I just wondering. Perhaps 4 and 2 and 4 are not independent either.
Probably not.
Yeah. Can we try? Can we solve the
What's that?
B in terms of D, or can we
Yeah.
solve
Hmm.
these two are must also not independent? So
Yeah. Oh, oh, come on.
so D equal to B. Yeah, D equal to B.
Yeah. So it's oh yeah.
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 That's very interesting. I think we encounter that issue that when you have the dependent equations, right? Then you got to
Yeah.
decide. But this relation is fixed, right? So basically, if we can,
Yeah.
in other words, but we still have no relation between C and D, right?
Between C and D,
Mm-hmm.
you could try and figure it out. You'd have to use. Oh, actually, no, you
You
can't.
don't. C and D.
Yeah, you can't because there's no like equation with both of them.
Yeah.
Oh,
Well, that's the issue. Yeah, that's the issue. Quite unexpected, but today's idea is that you can we just go to recap what we have done today. So
yep.
yes, but so basically, yeah, because you want suggest to give you a summary. So basically, we for the given vectors, right? We know there exists an eigenvalue and eigenvectors.
Eigenvector.
Yeah,
Yeah, vectors.
the maximum number is equal to the dimension. Okay, 2 by 2. That is 2. Okay.
Yep.
So in other words, that is something. This is equation special. So sometimes, so in general, a matrix times a vector, you get a different vector. We have seen that several times, right?
Yeah. Yeah.
However, in this special case, instead of get another vector, you
Yeah.
got the vector just by with different magnitude. That's all.
So
that is a very important feature of the matrix.
Oh,
yeah.
It's just a vector with this. It's the same vector but different magnitude.
Different
applied,
magnitude,
right?
different apply. Yeah.
Like a different scalar.
Yeah.
Like a yeah.
So that is something you have to remember. Now, of course, by just use this equation, you should be able to solve both eigenvalue and eigenvector. Okay.
Yeah.
That's what we learned last time. But in addition, that is something very important. So in addition, we have learned today is that once we know that, because we know that, another thing is important. Where did we erase that. Okay, right down here. Yeah, right down here. It's just the same thing. So it's just as important thing. So for matrix, you will got a special transformation matrix. Okay, that will allow you after this transformation, because basically, by the way, this is transformation. So if you have, say, let's just go to next page. I'll just give you a summary of what we learned today. So basically, so if you have vectors, right, you can use the transformation. So normally what you get, this is called a transformation. You will get another vectors, right? Okay.
Yeah.
But if the B is a special, if the B is built by the eigenvalue, right, of the matrix A, confused?
Yeah.
If B, in this case, if B is built by the eigenvalues, this is x, y. Okay, right down here, so x2. Just write for short, right? Then you will get a diagonal. You get a diagonal. So you got lambda 1, numbers are 2, 0, 0. You see?
That's what C equals.
Yeah. So that is the essence of matrices. Okay, that's essence. So and so this is like if you so we put these two together. So if you have vectors, you have vectors, you multiply by matrices. Normally you get something different. Normally you get something different, right?
Yeah.
But in the special case, you get this. So this is how these equations are essential. I hope you will spend some time to figure out what does it mean. Okay.
So basically, when you have a vector multiplied by a matrix, it makes
you get different.
It creates a new vector.
Yeah, that's right. That's in general. Yeah. So, but like we talked about yesterday, last time, you see, if you have vectors, so for example, you have vectors. So I just do it quickly. So you have a vector here, right? If you multiply this with normally you will get something else. You will get something else, or even here, right? Or even here.
Oh,
okay.
But with the eigenvalues.
Eigenvalues, yeah. If it's eigenvalues, then they just stay in the same line, in the same direction. Can you see?
It's the same vector with a different magnitude.
Different magnitude. Is that interesting?
Yeah, that makes sense. Oh, that's okay.
So I think we will stop here. Shall we talk to Ryan today, or is he tired?
Yeah. Ryan's.
Yeah, because a little bit. I understand. Perhaps your mom is disappointed because the result for him is not high, right? Yeah. Doesn't matter. I will talk to him. I will talk after this. I will talk to him. Okay.
Yeah. No. Okay. We just told him we just want to talk with him, and it's just that he needs to do much more practice, in spare time. Yeah.
And because you are doing the same B with him, why don't you help him by yourself sometime? Okay.
No, I said I'm gonna try and work with him.
Just remind him to do daily exercise. That's why I emphasize. Okay, daily exercise. Yeah. Okay. All right. I will see you next time. I will talk to Ryan.
Okay. I'll see you tomorrow.
Yeah.
All right then.
Okay.
All right. Good night.
Bye.